All right. I want to go over a couple really important concepts when it comes to graphing. This is the non-technical part of the pre-lab, by the way. This is the part where I'm teaching you the science and a couple terms and a couple keys of good graphs. So let's take a look here. First of all, let's define a couple terms. Dependent variable and independent variable. And I always found these very, very confusing as an undergraduate because they never really seemed to make much sense. The independent variable is the one that you control, which I know sounds like a contradiction. It's independent, but you control it. It's the one that you're using to mark off the other one. For example, I've got a data set up here. And this data set measures the distance traveled by a car per unit of time. We're controlling the time. I know, it's like we have a TARDIS and we're Gallifreyan. If you understood that, we're going to be best friends. We're controlling the time, right? We're marking off time in increments of exactly 1 second. So that's independent. It's not depending on what we're monitoring in the experiment. Time does not depend on ethanol content. Correct? So our independent variable is what we control. Or what we're marking at controlled intervals, right? We control how often we measure time. We have absolute control over the independent variable, which always, again, sounds contradictory to me. On a graph, the independent variable traditionally goes on the x-axis. Then there's the dependent variable. The dependent variable changes in response to the independent variable. The dependent variable changes in response to the independent variable, or is measured as a function of the independent variable. For example, in this data set, we're measuring the distance our rocket travels as a function of time. We don't have a control over how far our rocket's going to travel. I should have said, this data here is a chart. And it's a chart of the distance traveled by rockets burning different fuels. So it's a measure of the distance traveled by rockets burning different fuels. And in our experiment, we're measuring the distance traveled every so often. We control how often we take our measurements. Since we control how often we take our measurements, that's our independent variable. What we don't control is the distance the rocket travels during that time. That makes it our dependent variable, because this depends, the distance the rocket has traveled depends on how long the rocket's been traveling. Do you see what I'm saying? The longer the longer the time goes, the longer the rocket's going to have traveled. Since the distance traveled depends on what time we're measuring at, it's considered the dependent variable, because it changes in response to what we're measuring, the independent variable. You could also view this data set as having two independent variables. We control the amount of ethanol, correct? So you could view that as I should have used red there, forgive me, as an independent variable as well. We control that, and we're measuring distance traveled per unit time as a function of that, right, based on 3 different data sets. But that's really higher order thinking. Matter of fact, maybe you're better off forgetting that I even mentioned that. So that's dependent variable, independent variable. Your dependent variable is generally on your vertical axis, or your y-axis, is what you probably called it when you went through algebra. All right, why doesn't everybody write down TARDIS? Everybody write down TARDIS, just based on the reference I made previously. All right. So those are a couple terms. Now let's talk about qualities of good graphs. There are several qualities of good graphs. The first quality of a good graph well, actually, let me rephrase that differently. The scale of the graph is appropriate. When you look at a picture, you want it to be as large as possible. Same for a graph. You make your graph as large as possible by choosing an appropriate scale. For example, if we look at our rocket data again, we're measuring time from 1 second to 10 seconds. So if I was plotting a graph, I might choose to make time and space out my ticks from 0 to 12. Make that graph as large as possible, or even 0 to 15. You want to make the graph as large as possible, but you want to make sure that all your points are on the graph. That's why you wouldn't go 0 to 10. For example, if I gave you this data to plot, and I saw that you plotted time from 0 to 25, or 0 to 20 even, I would count it wrong. If we looked at our distance traveled here, we have distances going from 0.35 meters for that one to 2 meters, and from this one it looks like 0.42 to 4 meters. So if I'm wanting to include everything on this graph, I would want to make my scale for my axis 0 meters to not 4 meters, to 5 meters, or even better, 4.5 meters. That way I could get my graphs as large as possible. What I wouldn't do is if I put it 0 to 10 meters, that would be wrong, and I'd take off points for it. You want your picture to be as large as possible on that graph. Now, the great thing about using Excel is Excel will usually make your graphs appropriate for you. Let's take a look at how Excel graphed this data and some of the other qualities of a good graph that we can observe by looking at our Excel graph. All right, let's take a good look at this graph and all the things they did right and define some of the other characteristics of really good graphs. First of all, notice how they took full advantage of the space to make the graph as large as possible. They had time data going from 0 seconds to 10 seconds. So they made the graph go a little bit farther. Well, they had data from 1 second to 10 seconds. They made the graph go a little bit farther on each end to the 0 down here and then to the 12 over here. They didn't go to the 20 or they didn't even go to the 15. They allowed the graph to be as large as possible in this direction. They did the same thing on the distance. They had data going from, what was it, 0.3 to around 4. So they went to 4.5. They didn't go to 6. They didn't go to 10. They allowed this graph scale to be as large as possible. And that's what you want to do when you make a graph. Now, if you're doing it in a program, most programs will do this instantly for you. So that's what we were talking about when we talked about maximizing scale. Now, another thing that all good graphs have is they have axis labels with units. Any graph that you submit in this class should have both axi fairly clearly labeled with units. After all, telling me that you have distance traveled over here doesn't really tell me much. Is it kilometers, centimeters, picoseconds, picometers, light years? So it's important that you tell me it's meter. Same for time, right? Is it seconds, minutes, hours, days, years? So you have to have axis labels with units. Next, you also should have a title on your graph. Somebody should be able to look at your graph and know what it's a graph of. Effects of percent ethanol on rocket fuel on distance traveled by a rocket. Then I've got more than one line on this graph. You only need to do this if you have more than one line on a graph. But I clearly have more than one line on the graph here. So I need to have what's known as a legend. And I'm not talking Legends of the DC universe. The writing on that show is so inconsistent. Of course, they only made it at the last moment because it was supposed to be the Suicide Squad spinning out of Arrow. And they had to put the kibosh on that at the last moment when Warner Brothers planned the movie. Trust me, the Suicide Squad they had set up in Arrow was awesome. They'd cast people perfectly. Amanda Waller was awesome. They had everything all set, ready to go, and then the Warner Brothers movie people ruined it like they do just about every other DC movie. And I digress. And somebody write down Captain Jack. Oh, you've written down Captain Jack already? Somebody write down TARDIS. Everybody write down TARDIS. So you need a legend. And the legend tells what each of the different lines is. Here, we've got 10% ethanol represented by the blue, red, and purple. And you can see we also have our legend tells us the line of best fit. the linear line of best fit. So those are your characteristics of a good graph. Appropriate use of scales, clear axis labels with units, title on the graph, and when needed a legend telling you what the lines are. One other thing I want to do here is I want to talk about the equation a line gives you. Here we have the intercept set as 0, so our line only goes y equals 0.3607x. But I want to talk a little bit more detail about your general formula for a line. You'll remember from algebra class, y equals mx plus b. Let's review those parts. B is the intercept, and the intercept of a graph is where the line crosses the x-axis. Then you have the slope, slope is what we really want to focus on. Your intercept is often going to be 0 and not part of your equation. Y because at 0 time you often have very little, if anything, happening, right? Other times the intercept will be really important, but a lot of times it'll just be 0. Slope. Slope can be thought of as rise over run. You can think of it as the change in a y-coordinate divided by the change in the x-coordinate. Mathematically, I'm sure you're familiar with the concept that you're probably familiar with your algebra teacher telling you that the slope is y2 minus y1 divided by x2 minus x1. The slope can be very interesting because it's comparing the rate of change of your x and y's. It's comparing the rate of change of your independent variable to your dependent variable. It's measuring how much they change relative to one another. So it can be a very, very useful tool for a chemist. For example, in this lab, and I believe in this graph that I have, and I believe in your lab as well, it's actually your slope actually represents a rate. You can see that when you look at the units here. For this graph, we have y units of meters and x units of seconds. So your slope would have units of meters divided by seconds, which is literally velocities, right? Or literally speed. The larger the number of the slope, the greater the value of the slope, the greater the change in your independent variable, per a unit of your dependent variable. So if I asked you which of these ethanol mixtures made the rocket go faster, you'd look and see which of these had the which of these had the greatest slope. This one, R, 30%, had the greatest slope of all. And that was the last thing I wanted you to do, other than to write down Dirac. I hope everybody wrote down Dirac. Exterminate, exterminate.